Hello from Cambridge to wherever you are. My name is Daniel Freund, and I'll be talking about joint work with Sid Banerjee in the space of online stochastic decision-making. Of course, it would have been great to hold a physical conference here in Cambridge, but I appreciate the opportunity to present our work through this different format. In recent years, the Bayes and Profit framework has been introduced for stochastic online decision-making problems, like online knapsack or network revenue management. The focus of this talk is to extend this framework to some new settings. In particular, in this talk, we will focus on the well-studied online stochastic bin packing problem. Let me start by defining the model of online stochastic bin packing as we will treat it today. The problem proceeds over T periods. We're given a set of K different items, each with a size and a probability. In addition, we're given a constant bin capacity. Now, in each of the T periods, we draw an item I with probability proportional to Pi, and we place that item into a bin. Once an item is in a bin, we can never remove it. Our goal is to place the arriving items into as few bins as possible while respecting the bin capacities. That is, the sum of the sizes of items in a bin cannot be larger than the bin capacity. We are given the time horizon and the item types and probabilities, but we do not know the exact sequence of item arrivals. Now, in the model as I just set it up, I assumed a few things that we don't actually need in the paper. So we don't require the distribution to be IID, and we even allow for correlated arrivals. In fact, we also don't need to know the exact distribution, and it would be enough if we just have a single sample of the T arrivals. For the details of all these bells and whistles, I'll have a pointer to the full paper at the end of the talk. Now, as I said before, the goal is to minimize the number of bins that are used over the course of the time horizon to pack all of the items. The benchmark that we compare ourselves to is the so-called clairvoyant optimal algorithm that knows the exact sequence of items that arrive over time and packs them optimally. Of course, we can never do better than this benchmark, but we can bound the expected difference between the number of bins used by us and the number of bins used by this clairvoyant optimal decision maker. We'll call this difference the loss of the algorithm, and our goal will be to have this expected loss be as small as possible. Now, in order to characterize our results and also compare them with what exists in the literature, it will be useful to defend another concept, which is that of waste. Waste is defined as the amount of empty space across all bins that have been created. A classical results by Coco-Betty and Weber states that the waste in the clairvoyant optimal packing either remains bounded by a constant as the time horizon grows large, or it scales as the square root of the time horizon, or it scales linearly with the length of the time horizon. The prior results in the space have loss guarantees that depend on which of these three regimes we're in. For the bounded waste regime, Zurich et al. Proved that the so-called sum of squares algorithm obtains a O of 1 loss guarantee. So the loss relative to the clairvoyant is bounded by a constant. However, when the clairvoyance waste scales as O of square root t, then the relative loss of the sum of squares algorithm relative to the clairvoyant also scales as square root of t. Gupta and Radovanovic introduced an interior point-based algorithm that also achieved square root of t scaling for all of the regimes. Now, their algorithm does not require knowing the pi values, but still they get also only square root t and not constant loss across different regimes. Prior to Zurich et al., many other heuristics have been studied for the problem. All of these also had linear loss. Now, the main result I will introduce in this talk today is an algorithm that achieves a uniform loss guarantee regardless of which regime we're in, regardless of whether we're in the bounded waste regime or the linear waste regime or the perfectly packable regime. For any regime, we will achieve a uniform loss bound. The algorithm is based on the Bayesian profit framework that was developed by Vera and Banerjee. And we will call the algorithm the Online Clairvoyant Optimal Pursuit Algorithm, OCOP. Let me try to describe some of the ideas behind that algorithm to you. It is worth highlighting that many of the ideas really come straight from the analysis of Vera and Banerjee for the online knapsack problem. Now, in order to introduce these ideas, let's first consider a few different concepts. The first one is that of a bin configuration. If you think about a maximally packed bin, it can have various configurations. That is the number of items of each type in it. For example, a bin may fit a phone and a guitar, or it could fit a guitar and 2 staplers, or 2 phones or 2 staplers, or maybe some other number of items. But these are meant to be maximal sets of items that fit into a bin. And we will call these maximal sets configurations. Now, what the OCOP algorithm does, it pretends it knew all the remaining arrivals. It doesn't know them, but it pretends it does. In practice, maybe it knows the expected number of remaining arrivals and assumes that this is actually the exact number of arrivals, or maybe it has a single sample of a full sequence of item arrivals, or access to an oracle that can create such a sequence. Doesn't matter where it gets that from, but it pretends that the remaining arrivals are like that one sample. And in the formal proof, we require some concentration around this one sample to hold true. Then given these arrivals that we assume, the OCOP algorithm can solve the so-called bin packing configuration LP. Here we have a decision variable for each bin configuration that decides how often that configuration is used over the remaining time horizon to pack all the items. The LP minimizes the total number of bins created, subject to creating sufficiently many bins that all the remaining items, which we don't know, but we pretend that we do know it, can be packed in the configurations that are created. What we will need to know for each item after we solve the LP is the configuration that the item is used for the most, that is used for this item the most often in the solution to this LP. Given that, the OCOP algorithm proceeds as follows. Whenever it creates a bin, it already commits to the configuration that the bin will have eventually. So for example, here we had a stapler arrive, and we created a bin, and we committed ourselves to that bin being the configuration with 1 guitar and 2 staplers in it. Now at this point in time, in principle, we could still add a phone to that bin. It's just a bin with 1 stapler in it. But the OCOP algorithm doesn't do that. Instead, it just commits ourselves to the specific configuration at the time that it creates a bin. Now, when an item arrives, and we've already created a bin with a configuration that has space for that item, then we can just place that item into one such bin. For example, if we previously created this configuration with 1 guitar and 2 staplers, and now a guitar arrives, then we can add the guitar to that configuration. On the other hand, if we don't have any spaces reserved in the existing bins for the type of item that arrives, in this case, it's the phone that arrives, then we create a new bin for it. At that point, we solve the LP and check what configuration items of the current type, in this case the phone, go in the most often. Then we create a new bin and commit the new bin to that configuration and place the item in it. In this case, the configuration with 2 phones, 2 staplers. Now, how can we bound the resulting loss of the OCOP algorithm? To do so, we define the hybrid objective in period t as the optimal objective that the clairvoyant could obtain if we force her to follow the decisions that OCOP has made in all the periods up to time t. Then we can write the loss of OCOP relative to the clairvoyant over the entire time horizon as the difference between H0 and HT. H0 is the objective that the OCOP algorithm gets, because if we force the clairvoyant over all time periods to follow OCOP, then she will get the same objective as OCOP. And HT is the objective that the clairvoyant gets, because if we force her in no period to follow OCOP, then she can just do the clairvoyant optimal thing. Now, what that allows us to do is to write the difference as this telescoping sum of differences in subsequent rounds. And that allows us to focus on the loss that is incurred in each period. Crucially, in each period, the optimal objective changes by either 0 or 1. At best, the optimal objective is not affected by the decision made in this period. And at worst, we created an unnecessary bin that the clairvoyant can just ignore for the remaining time horizon. So what we'll want to do is to bound the probability that the difference is 1. Specifically, what we will show is that there exists a T0 that is independent of the time horizon, such that the probability of the difference being 1 is bounded by 1 over t squared for t greater equal T0. As a consequence, we can then bound the expected loss of the algorithm as the sum of 1 over t squared plus T0. And of course, this is a constant since T0 is independent of the time horizon, and the sum of 1 over t squared is at most pi squared over 6. Now, what remains to be done is the probability bound. How do we know that the probability of the difference being equal to 1 is actually small? For that, recall that HT plus 1 is only greater than HT if the decision in period T plus 1, in particular the configuration that we created or committed to creating in period T plus 1, implies that the clairvoyant, when forced to create that configuration, will end up with a greater objective. Now, what that implies is that the clairvoyant would not want to create any more copies of this configuration. On the other hand, we know from the way OCOP makes the algorithm that the LP would really like to make a lot more copies of this chosen configuration. In fact, we picked it because it is the configuration most frequently used in the LP for this particular item. What this allows us to do is to apply some classical sensitivity results in linear and integer programming. In particular, what is known is that optimal solutions to linear programming problems are continuous in perturbations of the right-hand side. So the right-hand side is the number of arrivals of each item here. Now notice that I'm saying it's the optimal solution that is continuous. It's not only the optimal objective. Now, for optimal solutions to the LP and the clairvoyant to be far away from each other, the real arrivals must then be far from the right-hand side that was used in the LP. With IID arrivals, as we've assumed for the purpose of this talk, we can use Chernoff bounds to guarantee that that happens only with vanishing small probability. Now, this event that happens with vanishingly small probability is actually necessary for HT plus 1 to be greater than HT, because otherwise the optimal solution to the LP, creating so many copies of the configuration that is chosen by OCOP in this period, would be large enough that the deviation in the solution space would be too small for it to cause a mistake for the clairvoyant. Now, there are various ways in which the results that I presented can be extended in interesting directions. As I mentioned before, we can change the arrival process quite flexibly. And in general, in the paper, we have general sufficient conditions and various generalizations of the vanilla bin packing problem that I described here. And all of these would still fit into our results. Another concern that one may have about the results is that they require a very frequent resolving of the bin packing LP. But actually what we show is that we can get the uniform loss guarantee even if we resolve very rarely, only in log t out of t periods. We also generalize the results not only beyond vanilla bin packing to other bin packing variations, but rather we give some fairly generic conditions for online decision-making problems for which the results hold. And finally, we also provide some necessary conditions showing that most of the conditions that we assume are not just byproducts of our algorithm design or our analysis, but actually hold for any algorithm to achieve a uniform loss guarantee. So to conclude, in our work, we generalize the Bayesian profit framework and characterize some of its limitations. And specifically, we derive a uniform loss algorithm for online stochastic bin packing. The full paper is available at the URL in the slide. And if there are any questions, we would be very happy to be contacted either at dfreund@mit.edu or at sbanerjee@cornell.edu. We hope that you will stay safe and healthy in these times and that you enjoyed our talk on the online stochastic bin packing problem.